welcome. Oh, no, that's all right. Does he let people drink in the observatory? In this bit, yes. I'm not sure about up there. Right, we're breaking the rules.
I'm Marnie Chesterton, host of Crowd Science, and for a previous episode on the BBC World Service, I climbed up to a little-known observatory in central London, partly to drink hot cocoa, but mainly to uncover the secrets of the universe.
If you look up, you can see it's sort of hazy. There are stars, you can see the stars, but it's sort of hazy. So that's just pollution in London. And it means that you can see bright things, but it's quite difficult spotting galaxies. Step on the planks.
The reason the Crowd Science team tackled ice-covered planks at night time was that listener Koon Hao from Singapore sent us a question, and we exist to answer your science queries. Here's a quick recap.
My question is regarding dark matter, and is there any way that we can understand it more and maybe find it useful for daily living?
Our quest to find Koon Hao answers took us down the deepest mine in the UK.
How deep is it?
It's 1.1 kilometres.
So how long do we have to spend in the lift?
7-8 minutes.
It's a long time in the lift, okay.
And we met Professor Catherine Fries from the University of Michigan.
And I'm also a guest professor at Stockholm University.
And how long have you been working on finding dark matter?
I have been working on it since I was a graduate student, so I'm going to say that was 25 or 30 years ago. Ooh, more than that. Okay, so don't tell people.
We asked Catherine what real-world applications might come from this search for dark matter.
You know, at this point I don't know what those are going to be, but the past history shows that there will be something really major that comes out of it. So I can give you some examples from the past. One of the big ones that came out of nuclear physics is MRI. So nowadays MRI is used in hospitals everywhere where my shoulder hurts. What's exactly going on? So they did an MRI of that. But that, again, was a surprising offshoot. It was based on detectors for nuclear physics, and they turned out to really change our lives from the point of view of health.
You can hear more on this if you go back and listen to that show. Just search for Why Does Dark Matter Matter in your podcast app. So that was then. Now, Crowd Science often turns into a kind of conversation with our listeners because episodes spawn more questions, and it turns out that you lot love a physics mystery. We received loads more emails with questions relating to dark matter. Questions that we're going to tackle today. To help me, I'm joined in the studio by two astrophysicists. Down the line from the University of Arizona is Buchin Mutlu-Pakdil, and sitting next to me is old friend of the show, Matt Middleton from the University of Southampton. Welcome to you both.
Thank you.
And right. Old?
Old. Old as in been on the show before.
Grizzled.
Yes. First, I think we need a recap on what dark matter is. Buchin, you first.
So most of the things that we see and we are familiar with is normal matter. And it is only 5% of the universe. So 25% of the universe is dark matter. That's the mysterious object. We don't know much about the nature. We cannot touch it, we cannot smell it, we cannot hear it, but it is there because we can see its gravity there. And the rest of the universe, the giant portion, is dark energy, which is much more mysterious than dark matter. We just know it is energy that makes universe expand.
Okay, so this stuff, dark energy and dark matter, it's most of the makeup of the universe, and dark matter is 5 times as much as all the stuff that we can see, the stars and you and me and everything.
And everything, yeah.
Everything that I'd consider to be stuff. Yeah. How do we see normal matter, like the microphone in front of me and you?
We see objects because of light, which is electromagnetic radiation. And we see objects because the light bounces off to our eye, and from that we can see the objects. But the dark matter doesn't have that effect. It is just transparent. It just goes through it. So because of that, we cannot see them.
So if you shone a light on dark matter, what would happen?
Go through.
Okay.
What we call the interaction, the ability for this dark matter to interact with anything is incredibly small, except we think via gravity.
So let's talk about gravity. Gravity is the attraction between two things that have mass. The reason we know that there's dark matter out there is because matter has mass. The bigger the mass, the stronger the gravitational pull. Our planet orbits the sun because the sun's massive mass pulls it into orbit. So we can't see dark matter, but can we see gravity? Yes, and a Swiss astronomer first noticed this whilst watching how galaxies move. His name was Fritz Zwicky.
There's a very famous scientist called Fritz Zwicky, and he looked at galaxy clusters. Now, galaxy clusters contain thousands and thousands of galaxies, and we think that these things should be essentially not flying apart. And so if you look at how fast they're going, you can work out how much mass there should be there. And Fritz Zwicky discovered that in order to keep them shuffling around all over the place and not flying apart, you have to have much more mass there than you could see in the stars.
I wanted to see this for myself, and so paid a visit to Professor Malcolm Fairburn. He's the one with a telescope dome on the roof of his university, King's College London.
Now, if you look up there, you'll see a cloud in the middle of the eyepiece, and it really doesn't look like very much. In fact, you might find it quite difficult to see it.
No, I can see it. Yeah, there's a fuzzy bit.
Mm-hmm.
Yeah.
So that's the very centre of the Andromeda galaxy.
Is Andromeda our closest?
Andromeda is the closest big galaxy. There's a few little ones that are closer. Well, there's lots of little, very little ones that are closer. But Andromeda is about the same size as the Milky Way. And Andromeda is moving towards us, I think it's about 150 kilometres per second. And we can use that observation to weigh the entire system. And the answer is that the whole thing weighs something like 5 million times the mass of the sun. And we can't see anywhere near that number of stars. So there has to be something else there. And we think that most of it is dark matter, see?
So there's a whole load of stuff out there that's stuff that we can't see, but we think is there.
Yeah, and there's lots and lots of other observations which suggest the same thing. From the smallest galaxies right up to the largest clusters, we see that on every scale we need something to explain how quickly things are moving around that we can't see.
Physicists like Malcolm have calculated the amount of mass in things like the Andromeda galaxy, and there's lots, supposedly there, that we can't see, hence dark matter. Burçin, can we talk about what dark matter might be?
There's a huge discussion about that. We really cannot say anything about its nature yet. So right now we have a promising hypothesis that suggests that it is cold matter, which doesn't refer to the temperature, but it is referring to the speed of that particle, which means it is moving very slowly, and based on these called dark matter idea, right now we could actually explain most of the observations that we have today.
Cold, meaning slow moving, dark, meaning can't see it, matter, meaning stuff with mass. The cold, dark matter hypothesis fits what we can see. But physically, what is it? This is where theoretical physicists come up with ideas that explain what we can observe. There are several competing theories with great-sounding names like WIMP.
Well, it turns out they're WIMPs, which I don't mean that they've got no sort of spine or, any fortitude. What I mean is they're weakly interacting massive particles, WIMPs. And our best guess at the minute is that they formed in the very, very early universe. Now, our universe went through something called the Big Bang. Okay, now the Big Bang was an explosion in space and time, of space and time, and it was really, really hot. Now the great thing about things that are really, really hot and you've got really high energy radiation is that you can spontaneously create matter out of radiation. The remnants of those particles are what we think is dark matter.
While Matt is busy thinking about what dark matter is, listener Gautam is thinking about what this mysterious stuff might contain.
Hello, I'm Gautam from New Delhi in India. My question for Crowd Science is this. If there is dark matter and dark energy, does it mean that there could be dark life too? So since I was, going through scientific stuff, and I realized that what you need for life is energy and matter. So now if there is dark energy and dark matter, it was one of those thought experiments. So since I couldn't find an answer, who better than to ask Crowd Science?
Who better indeed? And it kind of makes sense because the stuff that we're made up of is only 4% of the universe, and if the rest of the universe is dark, what's to say that there isn't something or someone somehow lurking out there?
Exactly. So if there is such a huge chunk that is absolutely unknown, why discount anything?
Do you imagine it as something that is around us, or is it in a galaxy far, far away?
No, it has to be around us. What we are given to explain is dark matter is everywhere. It's in this room, it's outside the room, it's everywhere. So if we are surrounded by it, we are living in it.
Just listening to what you guys are talking about, I was imagining something like a massive jungle all around us with dark lizards and
exactly,
dark,
yeah.
I don't know what else, flying all around us, and yet we're totally unaware.
Totally, yeah, exactly.
It's kind of nuts, isn't
Totally,
it?
yeah, exactly.
That was producer Greya and Gautam and me going through his thought experiment, which sounds very science fiction. But how much of it is science and how much of it is fiction? I've got two astrophysicists who may be able to help me. Matt, I'm going to come to you first because you are shaking your head and you have been all the way through our talk of feelings and lizard worlds. Go on,
I love feelings and lizard worlds. So
what do you reckon? If there is that much that we can't see, maybe there's all sorts of exciting things going on in it that we just can't see.
The answer is probably no, unfortunately. The reason for that is that life as we know it, complex organic creatures require quite complicated molecules and things like that. So amino acids, which are built of molecules, which are built of atoms, which are built of particles that have been glued together. Now, the leading contender for dark matter are particles which only clump together because they have mass. They don't interact in any other sort of way. So actually creating complex structures of the sort that produces life doesn't seem possible. Now, dark matter does form structures in the universe, but those structures are not sentient.
Buchin, if I can bring you in at this point, I mean, we're assuming that this life would be like us, but if dark matter is fundamentally different from normal matter, is there any reason to think it wouldn't be able to glue complex molecules together using another force?
For me, I feel like, yeah, it can be, but for us as a scientist, we need proof, maybe a signal that there should be an event that we cannot explain with our own knowledge. Then we could come up with hypotheses such as dark life. Then we would say that, okay, only dark life would explain this thing. But right now we don't have that.
Okay, so it might be possible, but there isn't any evidence or any theory by which it might be working or having any influence, so it's going to stay in the realm of science fiction for now.
Yeah, it is not a scientific idea, but it's totally a great idea.
Isn't it? Yeah.
Matt, anything to add?
I mean, you should never close your mind to ideas.
Yeah.
My view is no. From a scientific point of view, what we know about dark matter means that you could not form life from it.
We rang Gautam and played him the interview.
Hello.
Hello, it's
Good
Greya
afternoon.
and Marnie.
Hello.
Hello.
He has some poignant points that we want to share.
Well, all I can say that is, if dark matter wasn't there, the galaxies as we know them, they wouldn't be able to form. If dark matter wasn't there, the galaxies have the momentum that they would spin out of control. Now, if they would spin out of control, obviously, we would not have galaxies, we would not have stars, stars would not have planetary systems, And by extension, life as we know it would not exist without dark matter.
So that's an interesting point about life as we know it existing because of dark matter. But how do you feel about dark life as we don't know it, not existing according to the astrophysicists?
I think to give an absolute categorical refusal that dark life cannot exist is very unscientific. Since we know nothing about dark energy or dark matter, we may know a little bit about dark matter, but dark energy is absolutely dark. So to give such a categorical refusal that dark life is not possible, well, it seems very, very unscientific.
Well, I think everyone would be in agreement that more research is required.
Yes.
Gautam, thank you so much. I really appreciate your question.
Thank you so much. It was a pleasure talking to you.
You're listening to Crowd Science from the BBC World Service. This week, Marty Chesterton is finding out the answers to our questions about dark matter and dark energy.
If you have a question you'd like us to answer, you can send yours to crowdscience@bbc.co.uk. That's exactly what Yusuf did.
My name's Yusuf, and I'm from Utah in the United States of America. My question for Crowd Science is, could black holes make up some of the dark matter in our universe? So, yeah.
Are you particularly physics-minded?
Yeah, I work in aviation, so think about physics a little bit here and there.
Oh, cool. I don't feel like I'm qualified to be asking these questions on behalf of you guys.
Oh, either do I. It's
But it's fine. We're going to have two physicists in the studio, and I'm going to put your questions to them.
Awesome.
Matt.
So there's a competing theory to WIMPs, which beautifully is called machos. Macho. No, we're not doing it. Oh, you guys suck.
I mean, I just thought I'd let you sing a solo there.
Right, so machos are massive compact halo objects. So around our galaxy, we think there is a dark matter halo. And we don't really know what it's made of. What we do know is that when stars die, they form objects which typically are either really, really faint, so that we could never actually detect them if we looked for them. And black holes don't emit light either, so they're difficult to find. So for quite a long time, there's been this idea that maybe some parts of dark matter could be these very faint or completely black objects.
So Yusuf is right that black holes are contributing to the amount of dark matter, but do we have a figure? Do we know how much?
It's just incredibly small. I'm afraid I don't know an exact figure, but it isn't very, very much.
Is it like 1%?
I suspect it's lower than that.
Okay, back to Yusuf.
It feels surprising, actually. So I just thought of it, and I had no idea. I thought it was going to be totally wrong. So I feel pretty surprised, actually.
Where would you like your Nobel Prize to be sent?
Well, I guess I'd like to pick it up in person. So.
Oh, yeah, good point. So, as we've heard, dark matter makes up about 26% of the universe. The normal matter, the stuff we can see around us, that's 4% of the universe. So by my maths, that's a total of 30%, leaving 70% unaccounted for. Scientists call this segment dark energy. Do we know what it is? And if not, will we ever know? That's what listener Zazel got in touch to ask. And I'm here at the University of Cape Town in South Africa to try and find an answer.
Yeah, I'm Renato Costa. I'm from Brazil, and I'm doing my postdoc here at the University of Cape Town.
So, Renato, what is dark energy?
Yeah, if you think about the Big Bang and gravity the way it is, gravity is attractive, and if it starts as an explosion, all the matter is going further and further away, but it's attracting each other. So it should be decelerating, stop at some time. What we observe is the opposite. It's going further away and accelerating. So that's what we call dark energy. So I have here a very simple experiment to show that, which is a balloon with some dots on that. Okay. And like the dots are the galaxies we are observing, and the balloon itself is our universe. So if I blow this balloon,
So Renato's drawn some black crosses on an orange balloon.
Exactly.
And you've blown it up a little bit, and there's a distance between, I'd say, sort of a couple of centimetres between each.
Exactly. I have a tape measure here. You can measure that in centimeters.
Doodly-doo. Okay.
This is like
Four
centimeters.
centimetres. Okay.
Okay, so imagine that that's our observation now, and later in the day or in the years, I observe again, and then it's basically what's happening is the universe is inflating.
And now the distance between our galaxies is 7 centimetres.
Exactly, so that's the concept of dark energy. The thing is that we usually want to know more than just the observation itself. We want to explain that. And mathematics usually gives you the language to describe that deeper. And then you kind of lose track. It's exactly like if I start talking to you in German here, maybe you know German, but anyway, Portuguese, because I'm from Brazil. So if I start talking Portuguese, you're not going to understand it, which is completely normal.
I love it, though. We're getting into the realm of philosophy. It reminds me something. We did a programme on magnets, and I was desperately trying to understand electromagnetism and found it a huge comfort that Richard Feynman said, I can't explain magnets in any way that would make any sense to you. And I think he was just talking about, he could explain them, but it's in a language of maths, which works best written down, and it's not really a language of conversation.
Yeah.
Which is why, we're in a room with blackboards with all sorts of mathematical equations written down.
Exactly.
Not a great language for radio.
I agree.
Disappointing.
But we thought we'd give it a go all the same. Renato tells me that we don't know what's causing the universe to expand, but scientists have some ideas, and one popular one is that we need to modify Einstein's theory of gravity, tweak our equations, so to speak. That sounds easy, but it's not.
But also, not only that, you have to recover all the successes from general relativity. Because some people propose modified gravity theories that explain dark energy, but messes with all the other successes of general relativity.
So Newton's theory of gravity explains most of the stuff that I can see.
Yeah.
Einstein's explains even more.
Yeah.
People, when they're trying to modify that to explain dark energy, haven't come up with anything that doesn't mess with the building blocks that we've already explained.
It usually is easy to explain dark energy, but you mess with everything else at the same time. To modify that, it's not an easy task.
At this point, I'd like to introduce crowd science listener Lawrence. He's come up with a different theory to explain dark energy.
My name is Lawrence. I'm from the Canary Islands. I was actually born in New Zealand, but I've lived in Europe most of my life, and I'm now a Spanish citizen.
Great. And what is your question for crowd science?
My question is, could the effect that we perceive as being caused by dark energy have an origin outside our universe? Is it possible that our universe, although vast, is merely a bubble in something much more extensive that surrounds it and beyond the limits of our perception? And that, as the matter in our universe expands within its bubble and gets nearer the limit, the mass outside exerts a greater gravitational pull on it and causes the rate of expansion to increase.
So when people talk about the Big Bang, it makes you think of our universe as an explosion, expanding out into the void. What Lawrence, who's a maths teacher, is suggesting is more like our universe is an air bubble in a massive block of Swiss cheese. So that means that there's a huge amount of matter surrounding our bubble, and as we've established, more mass means more gravitational pull. So the huge amount of mass outside our air bubble universe could be pulling the universe apart. I put the Swiss cheese theory to Renato, who drew me a diagram to help explain that the idea of forces pulling the universe apart doesn't add up.
We draw this overdensity everywhere, or the circle of extra matter outside the horizon. And what I'm saying is that it's not possible because gravity will pull in all directions, actually, exactly equal. So this will stand still, it's not going to move.
So it's the material from one side is going to pull us, but the material from the other side is going to pull us.
Exactly.
And in conclusion, we won't go anywhere.
Exactly.
Gotcha.
Nothing will move. We'll be exactly compensated from all the sides.
So the only real way of explaining the acceleration of the universe, as far as you guys have worked out, is that it's something between the galaxies that is pushing everything.
Yeah, it's something from inside. It's not something from outside.
That's a shame, because I really liked Lawrence's theory.
It is a good one.
Yeah, of course. Why are we looking at all of this stuff that's being made inside space? Actually, maybe there's just something outside that we can't see that's pulling everything.
Exactly. I thought about that as well, and I was like, oh, that's a good thing to... Why not? Then I got the answer, so cool. But it's not that simple, so it's a very good question.
In summary, dark energy could be a modified theory of gravity, but it needs to work with Einstein's and Newton's explanations. And if this is the answer, no one's come up with it yet. Sadly for Lawrence, Swiss cheese theory is wrong. Our universe is expanding and pushing apart, not being pulled. But this isn't the only idea. There are loads of theories on this, because dark energy is even more of a mystery than dark matter. Maybe dark energy is a fifth force to add to the 4 fundamental ones we have in the universe. But back to Zuzelle and other listeners who want answers. Will we ever know what it is?
But South Africa itself has the SKA, which is the Square Kilometre Array, which will be the largest radio telescope on Earth.
And that's going to test dark energy theories?
Yeah, that would be great for testing dark energy theories and the dark energy itself.
Do you think you're going to get an answer in your lifetime?
Oh, well, I would say that for the new generation that wants to study physics and cosmology or astrophysics, the 2 biggest problems is dark matter and dark energy. So that any person that is willing to study these things should attack these problems.
Thanks to Renato Costa in Cape Town and his balloon-blowing universe. Also thanks to our studio physicists Matt and Bauchin. I had one final question for them, which is, why is finding dark matter and dark energy important?
Because my universe is full of them. We really understand. We really want to know what is going on in the universe and how the universe works. So to really understand what's going on in everything, in universe, in galaxies, we really need to understand the nature of the dark matter. With the current models, we have a nice picture that explains most of the stuff that we see, but still it's not enough. Without the nature of dark matter, we are facing lots of problems in our observations.
So I completely agree that understanding dark matter is really important. It's important for particle physicists and it's important for astrophysicists, and it's kind of important for us as well, because the stuff that's in the universe, so normal matter, radiation, dark matter, dark energy, if you add all of that up, that tells us what's actually going to happen to the universe. If there's too much stuff, the universe will end up contracting back onto itself when it was something called a big crunch, and that's where everyone gets really, really close together and really, really hot and everyone dies. Or maybe there's not enough stuff, in which case things start flying apart and it ends a bit sad, everyone gets a bit cold, and the universe dies that way. So understanding and weighing that stuff is really, really important for the fate of our universe. Is the fate of the universe a big enough reason?
Yeah, that's a pretty big and depressing reason.
Depressing? Okay,
I mean,
cool.
It ends in death, doesn't it?
Well, doesn't everything? Okay, wow.
But just to reassure people, this isn't happening in the next 4 to 6 years, is it?
Promise nothing. I want people to be phoning in and saying that the universe is going to end. No, not for a very, very, very long time.
We're talking millions, billions.
Numbers that are so big it shouldn't worry you.
Okay.
Yeah.
Phew.
On that optimistic note, that's it for Crowd Science this week. So, what have we discovered from testing listeners' theories? I'd like to bring producer Greya in at this point. Greya, what have you learnt?
That we really don't know much about the vast majority of our universe. That's my take home for today.
I'd like to say something concrete, so I'm going to go with that dark matter is probably a particle and that there are many hypothetical candidates, but WIMPs are the ones that most scientists are betting on. But anything is, of course, possible until scientists can confirm one. Dark life, on the other hand...
Oh, I was so sad when Matt was just categorically like, no, this is not possible. I really wanted there to be something out there all around us with the dark lizards and the dark jungle all flying around us.
But of course, for a lizard, maybe you need a multicellular organism, and so you need atoms to stick together, and that's exactly what Matt's saying is not going to happen. And then, of course, there's dark energy too.
I just think there's so much more about our universe that we need to understand, and it's fascinating. It's a great time to be a physicist.
Also, it's a great time to be a listener to Crowd Science, because we've dealt with quite a few listeners' theories this week, and I have to say, they've been really good, and do keep them coming. If you have any thoughts or comments, theories, suggestions, send them to crowdscience@bbc.co.uk. That's it from us. I'll leave it to our listeners to read the credits.
You've been listening to Crowd Science from the BBC World Service. One of the questions sent in this week is from me, Gautam, in India.
And me, Lawrence, from the Canary Islands.
And me, Yusuf from America, among others.
If you have a question you'd like the team to tackle, email it to crowdscience@bbc.co.uk.
This program was produced by Greer Jackson and presented by Marnie Testerton.
Thanks for listening, and goodbye.